this lecture, I'll talk about how to write matrix equations from a system of linear equations. Basically, a system of linear equations can be written in matrix form. That form is called a matrix equation. And these matrix equations will consist of several matrices. And so here's some vocabulary that you'll encounter. The coefficient matrix, the vector of unknowns, it's supposed to have an of in there, vector of unknowns, I kind of like that term, and the solution vector. It will also have an equal sign in it because it's an equation. And here's an example. This is a system of linear equations. 2x plus 5y plus 4z equals 4, and then you can see the other two here. These are in a special form, and the form is that all the variables are over here in the same order, x, y, z, and then the constants are written on the right-hand side of the equal sign. So it has to be in this particular form. Then you construct these matrices. All the coefficients, if I can highlight them, well, there's a 2, whoops, let me erase this. So here are the coefficients. There's a 2 here, a 5, and a 4. You pull those off and you put them as, if this is equation 1, this becomes row 1 in your matrix. Then I go to the next line. There's an invisible 1 here, then there's a minus 4 and a plus 3. Those make up the second row. Third row has a 1, a minus 3, and a minus 2, and there's the third row of this first matrix, and this matrix is called a coefficient matrix, or matrix of coefficients. And that's right here. If I have 3 equations and 3 unknowns, this will be a 3 by 3 matrix. If I had 4 equations and 4 unknowns, it'd be a 4 by 4 matrix. In more sophisticated examples, you might not have as many equations as you have unknowns, and there are techniques for handling that. But for this class, you will always have the same number of equations as you have unknowns. Now, go back here and look at the variables x, y, and z. They appear in, of course, every equation. Where they don't, you would have a 0 for a coefficient. But at any rate, you write those as a column matrix. And this is your vector of unknowns. And the third are these constants that are appearing after the equal sign. Those are placed in the third matrix, again after the equal sign. You see how we just transpose everything down here. And this is called the solution vector. Matrices with one column or one row can be called vectors. This is a solution vector. So here you have, again, this is your coefficient matrix multiplying the vector of unknowns equaling the solution vector. Oh, kind of missed that. Here's another example. I have 3 equations, and I really do have 3 unknowns, but they aren't appearing in every form. In fact, I just write this out. This could be 2x, and there's, of course, no y, so I could put 0y plus 4z, and that's what I'll have to do for the matrix. That equals 4. The next one, there's no x, so it's 0x minus 4y plus 3z. You see, I do have 3 equations. I have an x, y, and z, although not appearing in each one. X minus 3y plus 0z equals 5. You can't have an empty spot in a matrix. Everything has to have a number. And so where you don't have a variable, for example with that x, where you have the 0y, you must put the 0 here in the matrix. You don't have to write this out. There's no need to write this out. I'm just showing you how it is. Okay. But when I get to the second line, of course there was no x, so I put a 0 here in the matrix. The third one had no z, but I put a 0 for that coefficient. Other than that, it says before 2 and 4. 2 is a coefficient of x, it goes here. Then the 4 is a coefficient of z. Then we have minus 4 and 3 in the next row, and the last row is 1x minus 3y and then 0z. So there, this first is the coefficient matrix. Somewhere in the test, you're supposed to identify these. matrices. So that's your coefficient matrix, because these are all the coefficients of the XYZ. The second matrix is the vector of unknowns. And the third matrix, which occurs after the equal sign, that's your solution vector. As I mentioned on the first slide, you have to put the system of linear equations into a standard form. And in the standard form, you have to have all the variables on one side, equals, and then here are the constants over here. Whoops. These are the constants. I'm running out of virtual ink, I guess. Constants go here. And line them up. In this case, put the x's first, the y's second, and the z's third. It doesn't really matter what order you put them in, but you do have to line them up in some order, and it has to be consistent. Okay, you see what I did here? I just had to move the x and the z over to the other side, and that left it 0. 0 is a perfectly good number, and that's okay for it to equal 0. And here's a matrix equation for those for the equation, the system of linear equations on the previous slide. Now I want to show you how this works, and when you see how this works, you'll also understand a little bit more about matrix multiplication, because these matrices were not developed for, cost matrices for Walmart or something. They were developed from linear equations, and that's where some of these rules come from, or many of these rules come from. So here's my system of linear equations, 3 equations and 3 unknowns, and this is what the system looks like. Here's the matrix equation. I pulled up the coefficients and put them in the coefficient matrix. The next was the XYZ in proper order right here. Here's my vector of unknowns. Now, if I have those, I could do matrix multiplication on them. That means I would take the 2, 5, and 4, turn it sideways, and go against the XYZ. That would give me 2x plus 5y plus 4z, and then here's my equal to 4. I would do the same with the next line. The 1 minus 4 and 3 go against the xyz, and I get 1x and minus 4y plus 3z. I don't know where that came from. Then on the next line, I've got 1 minus 3 minus 2 go against that column xyz. I get 1x minus 3y minus 2z. Now they're equal. Remember, there's an equal sign to these constants, 4, 1, and 5. This is a 3 by 1 matrix. This is a 3 by 1 matrix. They have a chance to be equal. If they're equal, that means this must equal this. And it does. Here's my equation right here. So you see, by writing it in matrix form and then performing matrix multiplication, I get the original system back. What we're going to do with these matrix equations is use Gauss-Jordan method to solve them. But you have to see first where the rules for Gauss-Jordan come from, and they come from the rules that we use to solve a system of equations. And here are the rules right here. You can multiply or divide an entire equation, that means both sides of the equation, by the same number, of course as long as it's not 0. Right, that's a rule. I could take an equation and multiply it by 10 as long as I multiplied every single term and both sides of the equation. That's a perfectly legitimate operation to do. The second thing I could do is I could write equation 1 first and equation 3 second, and etc. It doesn't mean anything that one equation is the first equation and another equation is the second. They're just a group of equations. So I can switch the rows. I could switch the order of the equations. And the other thing I can do is add or subtract multiples of equations from each other. That's what we do in the method of elimination. So these are the 3 rules, and let's solve a sample system of equations using these rules. So we're just going to take a system of equation that has 2 unknowns and 2 equations in it, and here's our system: 2x plus 5y equals 28, 4x minus 4y equals 1, and we want to solve that. But what we can do is multiply the second row by minus 2. Remember, it's perfectly legitimate to multiply an entire equation by one number. So I would have the first row is the same, and the second row becomes minus 2x plus 8y equals minus 2. Now with the method of elimination, I now add them together, and of course I get 0 for the x's, which is my goal. My goal is to end up with one equation and one unknown. So I add them together, the x's drop out, I get 13y equals 26, and I can solve. I get y equals 2. Then I go back to the original equations with the x's in them and use that value to find the value for x of 9. So the solution for this is xy is equal to x of 9, y of 2. And I did it by multiplying the rows together, adding rows together. And here's a graph of what's going on. Both of these were linear equations. Here's the equation 2x plus 5y equals 28. Here's the other one of x minus 4y equals 1. Now when solved as a system, you want to find the point where they cross, if it exists. And in this case, the point where it crossed was 9 and 2, and you can see that graphically, although we found it algebraically using elimination. Now here's just a summary of this new vocabulary. The matrix equation is a way to write systems of equations in matrix form. And we're talking about linear equations, systems of linear equations, and we want to write them in matrix form. And it has 3 matrices associated with it. One is a coefficient matrix. That's a matrix made up of all the numbers that are multiplying the variables, the x, y, and z variables. Then there's a vector of unknowns. That's a column matrix, has only one column, and lists the variables in order. And then there's a solution vector, and that was the constants, and it occurs after the equal sign.